Okay, so let's continue. So the topic today will be Locally Linear Embedding, or LLE Part 2. Continuing with the Part 1 we delivered last time. So the literature we will discuss today includes these two papers. And they are kind of the very current development of the theoretical understanding of the locally linear embedding, which, as we discussed in the first lecture, is one of the very first algorithms in nonlinear dimension reduction. Okay, so recall the manifold model we will discuss. We will consider manifold without boundary. Okay, and this is a setup. Manifold d-dimensional, smooth compact, embedded in RP with matrix induced by canonical matrix on RP. And we do not consider boundary in this lecture. And this is a relationship. You have a random vector, okay, x, which gives you samples on the manifold. So this is x, and we make an assumption that the induced major, okay, is absolutely continuous with related to the volume form, and you have density function, and we assume this density function is sufficiently smooth. And this sufficiently smoothness is aimed for understanding the regularity in the locally linear embedding algorithm. And then with that model, we have the sampling. For example, we will sample n points IID according to x in this way. And if you have a function f on the manifold that is continuous, then we can do the discretization in this way. Okay, so the topic we will cover today will be the kernel analysis. We want to better understand what is the kernel associated with locally linear embedding. So recall what we discussed in the first lecture about the formula. So remember this Wi, omega I. Omega I is the barycentric coordinate of the point xi using the neighboring points. Okay, and the neighbor points are determined by all points within the epsilon neighborhood. And as we saw last time, when you have more and more points, then you will see that this quantity converges to the ratio. You have expectation of this quantity, this random variable, and this random variable multiplied by f of the random variable. This f is the function f, okay? And in the denominator, you can view it as the same as the numerator, but with the function f replaced by a constant function 1. And this guy, we denote it as an operator q of f evaluated at xi. Okay, so here x is a random variable, xi is a point we have interest to analyze. And as I mentioned, f is a continuous function. You have f arrow, which is a discretization. And remember, this ti is the augmented vector, and we write it in the continuous version. And this ci is the local covariance matrix in the continuous version. This IC, curl IC, this is a regularized inversion of the covariance matrix ci. Okay, and you multiply it by this quantity. So this is actually a vector. Okay, so that is a quick recall of the formula we have. And what we want to say is, what is the kernel? What is the kernel? So the theory you can check in the paper is, in the end of the day, if you consider this k LLE as the integral kernel for LLE, then you see this guy is 1 minus tx transpose y minus x times this truncation. And what is this term? If we come back to here, what we do is we collect this quantity, and we view it as a kernel. Okay, so this is that quantity. And you can check very quickly that this KLLE, this function, is actually a L2 function defined on MM, and is compactly supported. So very easily you can check that if you define A operator, then A operator working on F is defined as the KLLE, the kernel, acting on F, and the P of dy, this is the density function, density measure of the random variable x. Then this operator is Hilbert-Schmitz, so that you have almost everything you like. If you pay attention to this guy, you will see first, this function is actually not symmetric. You cannot say, oh, KLLE of xy is equivalent to KLLE of yx. Why not? Because here is a Tx transpose here. And this Tx transpose, this is augmented vector at x. So if you have yx, then it will be Ty transpose. So in general, they are different. In general, they are different. And also, you can see this guy. There will be also something different. Okay, so it depends on the point. It's not symmetric. Okay, second, you can see this kernel, which is very interesting. If you assume Tx is 0, suppose for some spatial kernel, Tx is 0, then you get 1 only, right? Then this is what? This is a 0-1 kernel. Because you put 1, in that case, you just put 1 over a local neighborhood ball, okay? Then this is 0-1 kernel. But now, you have txt. And this txt is what? As we will see in a bit, this txt, this augmented vector, actually captures the curvature. So actually what you get is a 0-1 kernel corrected by the curvature. And we will see why this is a curvature in a bit. But this is actually the kernel, or we call it LLE-kernel, associated with LLE algorithm. And there are some examples you can quickly see. Suppose you have M is flat and affine, then it is flat. So you can do a quick calculation and see that txt is actually 0. It's actually 0. There's nothing to do. So you get this expectation of txx is 0, and very good. You get 0-1 kernel. But if the manifold is a sphere, for example, SP-1 embedded on RP, then in the end, you will only get the normal direction. And you will see that txt will be a constant times upt. This x is in the North Pole, for example, and this up will be the unit vector point to directed to the piece direction, the normal direction. So in the end, you will get kernel LLE is 1 minus constant times upt y minus x. Okay, so this guy, as you can see very clearly, it will depend on the regularity, the regularizer C, which is the key step, as we mentioned in the LLE algorithm, and which tells you that this LLE kernel might be negative, depending on which C you choose. So this is an interesting example, and if we take a look, for example, this is a flat torus example. Then over this period, the kernel is flat, depending on the epsilon, depending on the C you choose. They're just flat. And this is the S2 example. You have this is the S2, okay, and this is the point. This figure is not very clear, but you can anyways see what it is. And then this is the neighbor point, and here is the kernel. You can see the kernel can become negative near the boundary. So in this case, by choosing a proper C the kernel may not be positive, and so that the LLE matrix may not be a random walk, which tells you that LLE algorithm may not be the same as what we thought in the beginning, that it is like graph Laplacian. No, it is not. It is not in general. So we want to take a closer look at the kernel. What is it? So this is the integral kernel, we saw it. And as we discussed, there is a specific quantity called Tx. This is an augmented vector. Then what is this guy? It is here, but how does it play a role? And if you remember, we have this Ti. Oh, this is T. This should be Tx. Sorry, this should be Tx, and this should be x. Okay, this should be x, small x. Okay, so this small x. Sorry, this is a typo. And this is small Tx. This is c small x. This is x, and this is x. Okay, sorry, this is a typo. So this is the augmented vector that we defined before. And what do you see if you remember? Cx is what? This guy is the local covariance matrix. And we want to study and want to explore a bit more about what this local covariance is and what information it gives us. And more importantly, you may see that, look, you have this pseudo inverse. And every time when you take inverse, you may want to pay attention, right? What about if Cx, this local covariance matrix, is degenerate or is not full rank, right? Then you take a pseudo inverse, you may run into some troubles. So this quantity already gives us a hint about what may go on, what may go wrong. Okay, so let's take a look. What is a local covariance matrix? So if you remember, we have one point xi, okay, and we have a G matrix, which is local data matrix. What is it? You take all the neighbors, there are capital N neighbors, and you just take all the neighbors and you subtract them by xi. That is your centralized. So this is a local data matrix. Okay, xi, and then this will be O, X, I, J, J from 1 to capital N. Local covariance matrix at xi is given by 1 over n, GG transpose, outer product, okay, which can be written as just the outer product. Okay, and when we have more and more points, n goes to infinite, you will get the convergence to Cxi. Okay, and Cxi can be written down in the integration form, which we saw, I think, in lecture 1, or maybe not. But anyways, we will see it in a bit. But there will be some convergence when n goes to infinite. And the convergence analysis result will be shown in a bit. So this is local covariance matrix. Why is it? And this formula, if you pay attention, you may see it looks very much like principal component analysis, like the covariance matrix we used in the PCA principal component analysis, right? So sometimes the analysis or eigenvalue decomposition of this guy and the embedding of local points, then sometimes people call it local PCA. Okay, so that is the terminology stuff. So now let's make some assumptions so that we can continue with the analysis and the results. So let's assume the manifold has been rotated and translated properly so that the embedding of the tangent space at x occupies the first d-axis of Rp. Okay, you can always do it because anyways, everything is local and it doesn't really matter where you are. Then by the perturbation argument, okay, if you have interest, you can see this paper for details, and we may have a separate lecture to discuss this perturbation argument in the future. Then this Cx, as I mentioned, this local covariance matrix at x in the integration form is the integration over a local bow. Okay, and you have outer product y minus x transpose. And remember here, y is a vector. Okay, x is a point, also a vector, and the py that is the density function and the dy. And here is a small, teeny tiny detail you want to pay attention. This ball indicates the Euclidean ball of radius epsilon centered at x. And why do we need to write things in this way? Because in practice, you do not have geodesic distance information of the manifold, so the only thing you can use will be the ambient space distance. So when you determine the neighbors or a small ball of radius epsilon, you always use Euclidean distance, ambient space distance. So that is why, in the end, we will have we do not have geodesic distance. Instead, we will have a Euclidean distance with the intersection with the manifold. And that will be the set we do the integration. Then if you do some expansion under this assumption that you have do the expansion, you have do the rotation translation, so that the sample x after the tangent space at x after the embedding will be located, x is located at 0, and after the embedding, the tangent space will expand the first d coordinate. Then this will be the result. What you get is you have some constant in front, and you have p of x, which is a density function, and you have epsilon d raised to power 2, and then that's the major term. You have dominant term, which has identity of d size d by d and all the other zeros, and then you have epsilon squared higher order term, fourth order higher order term, and the sixth order higher order term, etc. And we have to write down everything up to second order, fourth order, even sixth order, because we want to observe how will the regularization C play a role, which we will see in a bit. But no matter what you get is this is a constant. You can do this as a constant. Although this is very small, this is a constant. Okay, and this is a dominant term because all the others are smaller of order at least epsilon squared. So this is a symmetric matrix. All the others are symmetric. So you can do eigenvalue decomposition, and you get U lambda U transpose. This is the eigenvalue decomposition of the local covariance matrix. And now, suppose all these terms are gone. All these terms are gone, right? Then what you know is, we are doing eigenvalue decomposition of this very beautiful and simple matrix. Then everything is resolved. But now it's not, right? Because you have higher order corrections, and this will kind of change the behavior of the eigenvectors and eigenvalues of the dominant term. And what you can do is, again, run the perturbation argument and see that the eigenvalue matrix lambda is actually the same as this is a constant which we can ignore, and you see the diagonal terms will be identity plus higher order terms, and of that, and the other parts will be only higher order terms. And what you see is this is the tangent space eigenvalue associated with the tangent space, and this is actually associated with the normal direction, normal space. Okay, so pictorially, you will have a manifold, and this is a point x, and you have this is a tangent space, and you have normal direction. This is normal. This is tangent. Okay, and what we see is, because this is a manifold, locally, it is kind of just corrected by the curvature, but the curvature is it lives on a higher order term, and that is reflected in this expansion. And in the analysis later, we may just make an assumption saying, oh, the determinant of lambda 2 is not 0. Otherwise, it would be more complicated. And you can see the result shown in the paper. You can go to the paper and see the more complicated result. Okay, and on the other hand, eigenvectors. What will the eigenvector tell us? The eigenvector will actually give us an estimation of the basis of the embedded tangent space. And that is what it gives us. You have ux0. Ux0 actually can be written at x1, 0, 0, x2, and x1 is orthogonal of dimension d, and x2 is orthogonal matrix of dimension p minus d. What does it tell us? This x1, if you consider this x1, 0, this block, this d-dimensional vector, this will actually expand the embedded tangent space. Because you see, you have d independent coordinates, d independent vectors, and these d independent vectors will only occupy the first d coordinate. So this is actually the ground truth of the tangent space. Okay, or you can say it is a basis of the embedded tangent space. And this 0, x2, this is of size p times p minus d. Okay, this is a basis of the normal direction. Okay, so if you say we have ux0, which is a ground truth, but the true ux is actually the perturbation. Remember, we have to get some perturbation. We get some perturbation here. This is a perturbation. Okay, and this perturbation will change the basis, the eigenvector of I0, 0, 0, and okay, so I should put x here, ux lambda x, ux. So this is the notation issue. Okay, then this is the ux there, and this should be lambda x. Okay, notation. Okay, and then what you can say is, the true ux0, the true eigenvector, are kind of perturbed by an order epsilon square correction. And that is what it tells you. What we get in the end will be some kind of true tangent space and the true basis for tangent space and the true basis for the normal space with epsilon square correction, some small rotation in the end of the day. Okay, that is what it tells you, which makes sense, isn't it? Because when you do some local analysis, everything is like flat. Everything looks like flat, but it's not truly flat. It is kind of slightly perturbed by the curvature, by the local curvature. But local curvature is of order epsilon squared, so everything will be perturbed by some arrow of order epsilon squared. And then you can see some higher order and crazy expansion up to the 6th order. Okay, very good. So now let's finally can come back to see what's going on for this augmented vector. And there are some crazy calculation and the formula which you can see in the paper. I will not explain them. That is crazy, but yes, that's crazy. Its computation is very crazy. But no matter what, in the end, you will see the augmented vector can be written as I from 1 to r. What is r? R is the rank of Cx. And the ui is the eigenvector, lambda I is the eigenvalue. And you can see this, there is a ratio. And in the denominator, there is lambda I plus c. And what we know is the first d eigenvalues are associated with the tangent space, which are the largest eigenvalues. But the others will be smaller. So you can see, oh, then how do you choose C? Depending on how you choose C, right? The ratio may have different quantities, may have different impacts. So the normal direction might be enhanced if you do not choose C properly. That is what it tells you. And we have to be very careful because lambda 1 to lambda d, they're of order epsilon d minus d plus 2, but starting from d plus 1, it has two order, all the eigenvalues are two orders smaller. Okay, and you can see this is a kind of complicated formula, but no matter how complicated they are, the key information is this lambda I plus c, how you regularize the eigenvalues. Okay, so what we see from this discussion is that in the end, the kernel is actually data-driven. It's data-driven. So recall, this is the covariant. This is the augmented vector, and this augmented vector captures the curvature, and the curvature and the regularizer are deeply intertwined. That is why the kernel depends on the geometry of the data and is even data-driven, which is very interesting, isn't it? Okay, and this is a kind of a slight out of the topic, but interesting fact, which you can actually use the covariance matrix work we have discussed to design a better geodesic estimator. So traditionally, as I mentioned, we actually do not have an access to a manifold. So if you want to evaluate 2 points x and y, their distance, the only thing you can do is you use x minus y. This is the geodesic distance. This is using Euclidean distance to approximate the geodesic distance. Geodesic distance. But how well you can approximate the geodesic distance by the Euclidean distance? How well you can do it? The answer is here. There is a correction. You can use Euclidean distance to approximate the geodesic distance t when geodesic distance is very, very small, very, very close. Then you can well approximate them, but with a third order correction. This is two orders higher than t. And you can only do it when the distance, geodesic distance, is really, really small. Why? Because if the geodesic distance is very, very long, for example, you have a manifold that will wind back here, then you want to calculate the geodesic distance in between x and z, and you use the Euclidean distance, which is obviously underestimate the true geodesic distance, isn't it? Right? So this is totally wrong if z is far away from x. So if you take a look at this picture, you can see what's really going on. Suppose this M is a one-dimensional manifold. Okay. And what you can see is actually if you do some correction, using the normal direction, which I will not go into detail. We will have a separate lecture discussing how to analyze the local covariance matrix and everything, including Hessian and so on. Then you will see that by collecting things in this way, by correcting this distance in this way, using the normal direction, actually you just correct the normal direction a bit. Then you can get a higher order and a more accurate geodesic distance estimation locally. And because locally it is better, and this is a result, this is geodesic distance globally, and this is, this is geodesic distance estimation using just the Euclidean distance, and the red one is using the correction. Okay, then you can actually design a more reliable global geodesic distance estimation by using the minimal spanning tree algorithm and so on. However, this topic is kind of, well, on a theoretical level, it's not practical at all. So how to really make it practical? That will be the topic we need to continue in the noisy data. Okay, so I think that is it.